The recently obtained image of the interstellar object 3I/Atlas, captured by M. Yeager, G. Riemann, and E. Prosperi on November 20, 2025, has generated substantial interest and curiosity due to the appearance of unusually straight, narrow, and extended features emanating from the object. The photograph, constructed by stacking 20 individual exposures of 100 seconds each, reveals a remarkably detailed view of the object at a distance of 326 million kilometers from Earth. The field of view spans approximately 16.7 arc-minutes on each side, which corresponds to roughly 1.6 million kilometers across at the scale of the object's current location in the solar system. What stands out immediately are two slender lines extending almost 1 million kilometers from the object, positioned nearly vertically relative to the axis defined by the Sun, 3I/Atlas direction. These lines, observed alongside the typical dust tail and anti-tail that naturally align with the Sun's radiation pressure direction, form an X-shaped geometry that looks both unusual and, in many ways, puzzling. The first and simplest explanation for these linear features is that they might be accidental artifacts caused by a communication satellite orbiting Earth. Satellite streaks appear frequently in long-exposure astrophotography, especially with the increasing number of spacecraft in low Earth orbit. Because the image here stacks 20 long exposures, any fast-moving satellite crossing the frame in even a fraction of those exposures could produce the straight, narrow, consistent streaks we see. The fact that there is another faint line near the bottom of the same image strongly reinforces this interpretation, as the presence of multiple streaks in one set of long exposures would be entirely consistent with the behavior of satellites or space debris that happen to intersect the telescope's line of sight. Nevertheless, the possibility remains intriguing that these elongated features may be real physical structures originating from 3I/Atlas itself. If subsequent images taken from different telescopes, locations, and times reproduce these same vertical extensions aligned with the object, then we must confront the implications that they truly belong to the interstellar visitor. If the lines are real jets or outgassing structures associated with 3I/Atlas, then they raise two important scientific questions. The first question concerns their astonishing straightness and narrowness. 3I/Atlas has been previously reported to rotate with a period of 16 hours, which is relatively typical for small comet-like bodies, but still long enough that any gas or dust expelled from its surface would naturally be influenced by the object's rotation. Gas sublimating from volatile ices, at the current distance of 3I/Atlas from the Sun, is expected to have a thermal velocity of around 400 meters per second. Over the course of its rotation, this gas stream would normally show deviations or periodic wiggles imprinted onto its morphology. These wiggles would form because the jet direction would shift as the body rotates, causing the expelling material to trace a spiral or oscillatory shape rather than an extremely narrow, perfectly straight line. Based on the expected velocity and rotation rate, such wiggles should occur on scales of tens of thousands of kilometers, making them easily detectable in an image where features extend nearly 1 million kilometers. Yet none of these expected modulations are visible. The jets, if real, appear pencil-straight and remarkably uniform, a characteristic that argues strongly against normal cometary behavior. The second major question concerns the unusual orientation of these jets. Standard cometary physics predicts that volatile materials sublimate most strongly from the portion of the object facing the Sun. This geometry creates a dominant tail pointing away from the Sun due to the combined effects of solar radiation pressure and the solar wind. These forces nearly always align any dust or ion tails along the axis defined by the Sun-comet line. However, the lines emerging from 3I/Atlas in this image appear nearly perpendicular to that axis. They extend vertically relative to the Sun object direction rather than radially. If these lines were indeed activities originating from the surface of the comet-like object, they would contradict the typical physics expected for a body exposed to sunlight. Solar heating does not normally produce jets perpendicular to the sun-facing direction. Therefore, if these sideways jets are genuine physical phenomena, They cannot be explained by ordinary sublimation processes. This leads to the speculative, but physically grounded possibility that the lines represent the trails of small mini-objects or fragments that have separated from 3I/Atlas and moved away in straight-line trajectories. These hypothetical fragments, if they departed near perihelion, the point of closest approach to the Sun on October 29, 2025, would have had about 22 days to drift into their current positions. If they traveled a distance of about 1 million kilometers in that time, their average relative speed would be roughly 500 meters per second. This velocity is somewhat consistent with the speeds associated with natural breakup pieces of a comet nucleus, especially if they were loosely bound fragments or chunks of volatile-rich material ejected by internal pressure, thermal fracturing, or sublimation-driven explosions. However, this scenario also invites the more speculative interpretation that the fragments might not be natural pieces, but rather engineered components or compact probes released from a larger object, potentially representing technological fragments of an artificial interstellar craft. Though speculative, the scenario is not strictly impossible and has been brought up in the context of various anomalous features observed in interstellar objects such as Oumuamua and now 3I/Atlas. The possibility of artificial components becomes somewhat more compelling when we consider the earlier high-rise image captured at the time of 3I/Atlas's close approach to Mars on October 2, 2025. That image displayed an X-shaped glow around the object, which could be interpreted as the early beginnings of fragmentation into multiple discrete parts. At that earlier time, the apparent extension of the X-shaped pattern was only a few thousand kilometers, considerably smaller than the million-kilometer extension seen now. If the breakup began around the time 3I/Atlas passed near Mars, then the fragments would have had around 2 months to travel to their current separations. For a displacement of this magnitude, the required relative ejection speed would be about 200 meters per second. This is a relatively modest velocity when viewed through the lens of propulsion physics. Chemical rockets, whether natural or artificial, can easily impart a delta V of this magnitude. In contrast, tidal forces from the Sun acting across the diameter of a small interstellar object are much too weak to provide such a velocity kick. This makes a spontaneous tidal breakup highly unlikely. If the fragments were created by natural processes, such as internal pressure buildup or structural failure caused by thermal stresses during perihelion passage, one would still expect the resulting trails to gradually curve under the influence of radiation pressure, solar wind, and the object's rotation. Their alignment would not naturally form rigidly straight features orthogonal to the Sun-object axis. Yet the observed lines appear rigidly straight, stable, and remarkably narrow over immense distances. That level of symmetry and consistency would be considered unusual even for cometary fragmentation. By continuing to observe the object over the next several weeks, astronomers should be able to determine whether the features persist, and whether the detected lines move together with the interstellar object or fade as satellite streaks do. If the structures remain fixed relative to 3I/Atlas as it travels, and if they evolve in ways consistent with physical ejected material, then the hypothesis of mini-objects would gain credibility. Monitoring how the brightness, shape, and orientation of these lines change over time will help distinguish whether they are purely observational artifacts or real phenomena emanating from a dynamic interstellar body. Overall, the new image of 3I/Atlas has opened a compelling set of possibilities. It could represent nothing more than a coincidental alignment with human-made satellites, producing misleading straight lines through long exposures. Yet if the features turn out to be intrinsic to the object, they may signify a form of activity never before seen in a natural comet-like body. Whether the cause is natural fragmentation under unusual conditions or something more exotic involving technological components, continued observation will be essential to understanding the true nature of this interstellar traveler and the peculiar features now seen emerging from it.